In this video, I want to introduce the idea of least squares regression and talk about how linear algebra is connected with least squares regression. If you've seen this before, you might think of it as a statistics topic, and it is, but it turns out that in a lot of situations, the correct way to think about this is as a linear algebra problem. In this video, I'm not going to explain how to solve a least squares regression problem from start to finish. That's in a later video. What I want to do now is talk about what's going on in the background, how linear algebra is connected, and how we should think about this. So I have kind of a classic least squares regression problem in front of us. So I have 11 students, and I have their average quiz score in a class and their final exam score. And what I want to do is I want to figure out some sort of way to predict a student's final exam score from their quiz scores. And I'm going to try to do this by modeling it with a straight line. And to understand why I'm doing this, let's look at a picture. So here is a graph with all 11 points here, right? So you can see the point with quiz score 80 and exam score 72 is at the x value of 80 and the y value of 72, and so on for all of these 11 points. So I have 11 points in this, what's known as a scatter plot. And when I look at these, it does look like there is some sort of bottom left to top right pattern. And so it's reasonable to think that I can model this with a line. So if I draw on a line here, this is what's known as the regression line. I can't draw a line through all the points, right? They don't fall on a line, but this line is in some sense the closest line to all of these points. So in what sense is this the closest line to all of these points? Well, if I draw in vertical lines connecting each of these points to my regression line, these blue distances, this regression line minimizes these blue distances in some way. And in particular, it minimizes, so the regression line minimizes the sum of the squares of the vertical distances. So what I'm saying is that I could draw lots of other lines on this graph, but all those other lines, when I measured the vertical distances to the actual data points and squared those things and added them up, I would get something bigger than this line. So in some sense, this is the line of best fit. It's the closest line, and this is the regression line. The question is, how do I figure out the equation of this regression line? And in order to do that, that's where linear algebra comes in. We want to view this problem from a linear algebra perspective. So you might think initially, okay, this is a statistics question, right? We're trying to take some real world data and model it mathematically. And it is a statistics question, but in statistics, there's always underlying theoretical mathematics. Your next thought, which I know was my next thought when I first saw this, was that the way to solve this would be calculus. And the reason that calculus jumps out at me is this word minimize. Right? If I want to minimize something, I think, all right, well, I'll set up an equation, I'll take the derivative, I'll set it equal to 0. It's an optimization question. And we can solve this using calculus. That's true. And it turns out that calculus often is a good approach to solving these sorts of problems. I'm not saying that calculus can't help us out here, but it turns out we can also solve this with linear algebra. Often linear algebra is the better approach, and certainly linear algebra gives us much more insight into what's going on here than trying to solve this with calculus ever could. And that's what I want to explain now, is what does linear algebra tell us here? Because in particular, it tells us a few things. It tells us, why are we talking about vertical distances? Right? Why not just distances? Why not, instead of dropping vertical lines, why not drop lines that hit the regression line at a right angle? And why are we squaring these things? Why is that what we're doing? Why not just take the absolute value or something like that? So I want to view this from a linear algebra perspective and see what's going on. Because this statistics perspective has drawn this as a two-dimensional problem And what I'm going to do is I'm going to take some linear algebra and say, let's overcomplicate this and then make it way simpler. I'm going to say, look, this isn't actually a two-dimensional problem. This is really an 11-dimensional problem. Because another way of phrasing this question is, look, I want an equation of a line, y equals mx plus b, and I want that line to contain all of these points. Now, the quiz is predicting the exam score. So the quiz is x, the exam is y. And so I want, for instance, if y is 72, I want this to be true, right? And I also want if y is 71 and x is 68, I want a true equation. All the way down to the final one is if y is 92 and x is 88, I want all these 11 equations to be true. And I realized, wait a second, this is a system of linear equations. Let's rewrite this just so it looks a little more familiar, right? Let's put our y values over here. I have a system of linear equations, and it's 11 equations in two unknowns, m and b. And so we don't really expect it to have a solution, right? It doesn't. There's no line that goes through all these points. But so that's kind of the linear algebra view. Is okay, right? We have 11 equations, two unknowns. It doesn't have any solutions. Let's take it a step further. Let's go deep into the linear algebra. I'm going to write this as a matrix equation now, and I don't know why I scrolled so far down. I still want these numbers, but as matrices, I have this matrix A, and so the matrix A is going to consist of the coefficients or the values, and I have my matrix of my vector of m and b, and then I also have my y values. I shouldn't call this thing x because I already have x meaning something here. So let's call this c. And my y values are all the way up to 91. And I can rewrite this whole thing as a times c equals y. This may look a bit weird, but when you multiply each of these out, right, this column is the x values. And so m gets multiplied by that. We're multiplying x by the slope. This column of ones is just representing the fact that we always have a y-intercept multiplied by 1. Right? In all of these, the coefficient on b is 1. And then these are just the y values. Okay, so linear algebra perspective, we can go a step further than saying there's more equations than variables. I'm going to say something like this. This equation doesn't have solutions. Why not? Because y is not in the column space of A. An equation like this has solutions exactly when the vector on the right-hand side is in the column space of the matrix on the left-hand side. And this y value is not in the column space of A. So I'll show you a picture of what that looks like. The y value not being in the column space of A. It's this. So the column space of A is this gray plane, and this blue vector is y. And it's not in the column space. And you might say, Scott, this is not true. You're showing me a picture in R3, but we're not in R3. We're in R11. Right? Y is an 11-dimensional vector. And all of these vectors are 11-dimensional. And my response would be, you're right. You know, like what I'm talking about is not literally true, but the column space is two-dimensional, right? There's two vectors that span it. And So the picture I just showed you, which I'll pull back up, is not really that wrong. It's not totally correct, and we should kind of have a little bit of skepticism, but R3 is the biggest dimension that I can visualize stuff in, and so that's where I try to draw stuff. I mean, we do have a subspace, we have another vector in it, and so this picture isn't totally wrong. And what I'm going to do here is you have this what I'd call the kind of statistics or maybe calculus perspective, where we're saying, look, we're trying to make a line that's as close as possible to these points. I'm going to phrase it in a different way. I'm going to say, look, I'm not going to try to like make a line that's as close as possible to the points. I'm going to try to replace this vector y. So if I want this to have solutions, because it doesn't have solutions right now, I'm going to replace y with a vector that's actually in the column space of A, because then it will have solution. Now, what vector should I replace it with? You may see where I'm going with this. I should replace it with the closest vector. Right? If I draw this picture again, which I've used a few times, I should replace it with this purple vector because it's the closest vector in the column space. And what vector is the closest in the column space? It's the projection onto the column space. And I'm going to call this thing y hat, and it's going to be the projection onto the column space of A of this vector y. So I'm going to replace this set of y coordinates with something that actually will give us a solution. And we know how to do that, right? We know how to project onto higher dimensional spaces, or if we don't yet, we will know how to project onto higher dimensional spaces. I forget where this video goes in the order of things, but certainly we'll have a tool to calculate this thing. And then once we do that, we'll solve this new equation, which is not AC equals y, it's AC equals y hat. And then C will give us the coordinates, or not the coordinates, the values M and B, the slope and the y-intercept for the regression line. So we're taking a totally different perspective. Instead of saying we have a line that doesn't go through a bunch of points, we're saying we have a system of equations that doesn't have any solutions, and we're going to change it into a different system with solutions by replacing the right-hand side value with the closest vector that will give us solutions, which we get by projecting into the column space. And that's going to be equivalent to what we did in that other picture, minimizing the vertical distances. And this is where I really think that linear algebra starts to give you some nice perspective, is that why are we minimizing the vertical distances? Well, vertical distances are differences in y's, right? Y is the vertical axis in that picture. And so why are the distances vertical? That's why, because we're replacing this right-hand side y value with something. Why sums of squares? Well, distance in Rn is given by adding up the squares of differences. You then take the square root, but minimizing the sums of squares is the same as minimizing the distance. So the final thing I want to point out, so we have our new perspective. Hopefully that made at least some amount of sense. Once you work through a few problems, I think it's really nice. You start to see how this actually works out the same way. Hopefully that gives you a sense for how, this picture right here, we can think of as, no, what we're really doing is we're taking a system of equations that can't be solved, we're turning it into one that can be solved, and then we're solving that. One really nice thing is that it generalizes nicely. As we move up to higher dimensional problems, this sort of picture is harder to draw. But the linear algebra picture is not hard at all to draw. It just very naturally generalizes. So what I mean by this is, let's say instead, maybe what we're trying to do is we want to predict the price of a house, how much it'll sell for, and from certain values associated with the house. So maybe we want to predict the price of a house from its square footage, its lot size, and its age, how long ago it was built. So we have 3 inputs that we're predicting from to get 1 output. And we're not really going to be able to draw a picture of this, right? 3 inputs means that our inputs live in R3, and we have a single output there. And so unlike the example with predicting an exam score from quiz grades, where I was really in 2 dimensions, this picture would have to go in 4 dimensions, and it's going to be tough to figure out what's going on. But from a linear algebra perspective, it's not going to be, because we're going to be predicting the price as something times the square footage plus something else times the lot size plus something else times the age plus maybe a constant. Let's say this is how we're modeling it. And we're going to have a bunch of values of this, and it's all going to boil down to, we can view this as a system of equations that doesn't have a solution. We'll replace this side of things with the projection into the column space of our matrix, and then we'll be able to solve it. So this linear algebra perspective also really allows us to quickly go from basic linear regression, where we're predicting one variable from another, to multiple regression, where we're predicting one variable from a bunch of different variables. And as we'll see, lots of different formats of equations will fall nicely into this. It won't just be linear equations like this. Oftentimes, if we had quadratics or other types of things, it'll work very nicely.